Yeah, so for inviting and also for the introduction. So my name is Swaprava. So today we are going to look at something which we call mechanism design. You can also think of this as a inverse of the game theory. So just to maintain the continuity from yesterday's lectures, I will first do some amount of recap of what we did and then get into what mechanism design is, or where try to motivate you why it is needed. Okay, so just to give a quick brief introduction about my institute, it's IIT Bombay in better weather. So it's raining now, it's not this sunny, unlike the weather outside, but it's a very nice green campus, and it becomes even nicer when it rains. So we have an adjoining lake, so feel free to visit IIT Bombay at some point in your of your time, and also have a lot of sporting facilities. So after the students enjoy all these things, if they get time, then they also come to the lecture halls and study mechanism design. Yeah, so we have been doing good work at least. I hope that if you like the set of lectures, some of you will consider IIT Bombay as your master's program or PhD or even a postdoc position. Okay, so let's get back to the topic. So I'll do this transition from the game theory, which we discussed last time yesterday, and to where mechanism design, what mechanism design is and why it is needed. Okay, so I'm going to repeat one of the examples that was given in the Sushmita gave it as prisoner's dilemma. I'm just going to rephrase the name slightly, and you will see that why this this connection is interesting, and how that prisoner's dilemma game is even more general, where you can think about conflicts among countries or nations. So to do this, I need two volunteers. So maybe this part is, so this is a queendom and this is a kingdom. So I'm assuming that this is the queendom. So one queen from here. When you don't have to do anything, you just have to be the queen. So if you don't choose your queen, I'll choose someone. And one king from this side. Okay, so king. What's your name? Aryan. King Aryan. And queen? Okay, so I'll choose then you. So you are, yeah, so you. So your name? Shivani. Queen Shivani and King Aryan. So suppose you are handling a queendom and a kingdom, and the setup is that yeah, these are modern day kings and queens, so they can actually use AI, and they can use AI for two different purposes. Either they can develop better techniques, technologies for agriculture, or they can design better warfare machinery. Now, whichever they do, it has an implication, because the outcome will be decided, but not by what the queen decides or the king decides, but what both of them decide. So what is the meaning? So I'll fill this numbers, this boxes up with some numbers, and you will so try to associate these numbers. It's a tuple of two numbers. The first number refers to the utility or happiness of the first player, which is the queen here, and the second entry is the utility of the second player, which is the king here. Okay, so if both of them choose agriculture, then both of them become happy, they are prosperous, they have solved their food issues, so which is good. If both of them go for warfare, then they successfully defend themselves, but they don't grow as good as agriculture. Maybe they have a lot of loss of life, so the utilities there are significantly less. The interesting thing happens when one chooses war, the other chooses agriculture. Okay, so suppose player 1 chooses war, then what happens is they might, so and the other player chooses agriculture, then it will win the war. So of course, if they choose war, they will go for a war, and the kingdom will have no defense against them, because they have not invested anything. So for this example, I'll assume either you can choose A or W, not a mixture of them. So let's assume that for simplicity. If they choose war, then they can easily invade the kingdom, get all their agricultural produce, in addition their land and many other things. So the utility or the happiness that they get is higher than what they could have got in just their agriculture choice. the kingdom loses everything, so it goes down to 0, a huge loss for them. And the symmetric opposite thing happens when the queendom chooses agriculture and the kingdom chooses war. Okay, so is the game setup okay? Now we have seen last time, so just to remind you the notation, because the notation will be used. So here the players, and I will be denoting that as with n, which is same as what we have done in the in yesterday's class. In this case, this is a set of just 2 players, 1 and 2. The set of actions or the set of strategies, this SI, capital SI, in this case is A and W, either agriculture or war, for both the players, for both I equal to 1 and 2. Now once both the players have chosen their strategies, let us say the first player has chosen agriculture, the second player has also chosen agriculture, in which case the utility of the first player is given by this number 5, right. So this the first entry here. In this case, even the this happens to be the utility for the second player as well, and you can fill it up. Utility of A when so utility of player 1 when player 1 chooses agriculture, the other player chooses war, is this entry here, 6 sorry, agriculture comma war. Okay, so 0, right. So I think this should be clear. And yeah, so similarly the player 2 at A comma W will be 6, and you can fill the rest. So this is just to remind you the notation that we have used, and we will also use the same notation. Okay, so now you are discussing about what this is just the description. Now the king and the queen has to decide what you should do, right? And what was the conclusion last time, just to get that you have understood this game last time? If both choose agriculture, then is that a reasonable thing? So yeah, so remember that decisions are simultaneous, and every agent is trying to maximize his or her own utility. So they don't care about, the queendom does not care about what happens to the kingdom doesn't care what happens to the queendom. They are trying to maximize their own happiness or satisfaction. So think about it in this way, that suppose your opponent, so you are player 1, if player 2 chooses agriculture, then you see that this number, so your utility is 5 when you choose agriculture, utility is 6 when you choose war. So clearly this is better, so you will always gravitate towards warfare. If your opponent chooses war, then also it is better for you to go for warfare. At least you can defend yourself rather than completely being plundered by the other kingdom, right. So we have said this type of a thing, where the utilities are better for a specific agent irrespective of what other players are doing, right. What is the name of that strategy? That is a dominant strategy. So just keeping you yeah, so just reminding you that the utility of a specific player when you choose that strategy and other players are choosing some other strategy is greater than or equal to, yeah, I mean in this case it is strict, but we do not really need that, we will see. But the qualifiers are important, that this should happen for all S minus I in capital S minus I, and for all Si prime which is in Si, and of course for all agents, right. So if that happens, then we call this particular strategy as a dominant strategy of player I. Okay, so yeah, just remember this specific thing, that we have this true for every S minus I of the other players, right. And if that happens for every player, so suppose there exists a kind of a strategy profile. So a profile is nothing but a tuple of actions of all the agents. So let us say S1, I am just to denote it, it's a distinguished profile. So S1, S2. Suppose we have n players. In this case, n is equal to 2. So this, if you happen to get a profile where this S1 star is a dominant strategy for every player, for every agent I. So what is that kind of a profile called? So this is dominant strategy.
In dominant strategy, it is irrespective of what it is, so it should be S minus I dash, right?
Yeah, so I mean, I'm not saying anything about this, so you can choose whatever, because it's just a running variable. You have to do it for every possible thing, just like S minus I prime in this case can be agriculture or war. If there were more strategies, that was also included. But if this happens that this profile has, so Si star is dominant strategy for I, then it's not Nash equilibrium. That's what I want to emphasize. This is a dominant strategy equilibrium, much stronger than Nash equilibrium, because I'm coming to that Nash equilibrium, because you see the difference there. So what was the definition of Nash equilibrium? Sorry? Deviate, but under what condition?
Unilateral deviation.
Unilateral deviation. Think about that. So, so this is, so if this happens, then we call this a dominant strategy equilibrium. So understand these differences. Dominant strategy equilibrium. So it's a equilibrium which is different from Nash equilibrium. In Nash equilibrium, so I mean for pure strategy Nash equilibrium, which we discussed in the first part yesterday. So it is defined in terms of some profile. Let's say I have some this Si star, S minus I star. So just to maybe you have already you already know this, S minus I, the notation means that this is the profile of all the players except agent I. So if I just, let's say there is this I star here, I just remove that, and the rest of the thing is I'm going to call as S minus I star, just to yeah, I mean make the notation a little more brief. Okay, so this is pure strategy Nash equilibrium if there won't be any qualifier like this. So this is very important to remember, that you have the utilities. Now Si star, if everybody is playing at that equilibrium, then that is better than the any utility that you choose, let's say Si prime, but other players are continuing to choose what they were choosing earlier, right? So there is no for all S minus I, because this is a very distinguished S minus I star. Only for that I am saying that this inequality holds, and the rest of the qualifiers still hold, right? So this will still hold, and for all the players it will also hold. So this is PSNE, this is different. So is everybody clear about the distinction? So can you draw a kind of a connection between this?
Dominant strategy is always a Nash equilibrium.
Why?
Because like, it is for any general S minus I, but in the PSNE we have the specific S minus.
Does everyone agree with that? I mean, could understand that? So a dominant strategy equilibrium is saying, claiming something much more than PSNE. It is just saying that S minus at S minus I star, you will have this inequality satisfied, but dominant strategy has already that subsumed. I mean, in particular, if you put that S minus I star, because this is true for every S minus I tilde, you can also put something S minus I star, and it will also get satisfied. This condition will get satisfied. So the set of games, if you want to draw Venn diagrams, so the games with dominant strategy equilibrium, I'm just using a brief. So these are the games having dominant strategy equilibrium. That will automatically imply that those games also have a pure strategy Nash equilibrium. So you have also heard about the mixed strategy Nash equilibrium. So how will that the size or the Venn diagram of MSNE look like?
That will be bigger circle.
That will be a bigger circle, because PSNE is anyway trivially a and MSNE. Okay, the probability distributions are atomic and in that place. Okay, so these are the two things. So what kind of equilibrium do we have here? Nash or dominant? It's a dominant strategy equilibrium, because if you look at war, this is a dominant strategy for player 1, and this game is symmetric. You can also compare this number 5 with 6, because if player 1 is playing agriculture, player 2 can choose between these two things, and clearly war improves, and if it chooses war, this strictly improves. So yeah.
While defining dominant strategy, we are defining for each player, but we want it to be true for all the players. So we can, so every time if there is a dominant strategy, it will be present for all the players.
Right, very good question. So we are defining for a given player. So we just said that this is a dominant strategy for player I. It may so happen that for player J there does not exist any dominant strategy.
So we are saying for all I belonging to that.
So okay, so if that for J dominant strategy does not exist, then we can't say that there is a dominant strategy equilibrium. So you may have a dominant strategy, but I may not have a dominant strategy. In that case, there is no dominant strategy equilibrium. Okay, so yes, so this is saying something more, that if every player has a dominant strategy, only then you will have a dominant strategy equilibrium. If at least one player does not have a dominant strategy, then you cannot have a equilibrium.
So while defining only dominant strategy for one player,
It's
we will
fine.
just have the S tilde to vary from all the strategies. And
S minus I tilde. So
Yeah,
if
S
you are
minus
saying
I.
that your dominant strategy is for player I, then you will focus, so then that I is fixed, and you are looking at only this. You can vary the S minus I tildes for all the other players. This inequality should get satisfied. Okay. Then we will call that Si is a dominant strategy for player I, which is a distinguished player. Okay. So everyone is clear about this? Good to go? Okay, so as we said that this war is a dominant strategy equilibrium, and as we have argued, this is also a Nash equilibrium, pure strategy Nash equilibrium, but it's important to notice the difference, because that will be very important. Now what is collectively good? I mean, this is like bringing back some sort of a what we want as a society, as a citizen of the world. I mean, we don't really want people to fight among each other and get to a worse state of the world. Which one would have been collectively good? Like so agriculture is clearly much better, but it's not an equilibrium. You see this irony. Personal greed always drives you towards a situation which, so even if you write a contract, let's say this is something that you can relate to, right? So the countries write peace treaties and then they violate it. Right, so they can write peace treaty that will not go for war. They choose agriculture, but you see that it's better to violate that and go for a war, even if you write that peace treaty. Okay, so any questions about this game? Okay, so this is essentially prisoner's dilemma said in a different way, but you can see the connection. Okay, so let's look at a very different example, and this is where our design will be important. So suppose IMSC does not have such large campus that I can actually give an analogy, but let's say an university campus where these are the hostel blocks, and there are some 100 people who are taking bicycles to reach to the lecture hall in the morning. Okay, and naturally they want to reach as quickly as possible so that they can get more sleep. But the trouble is that these roads are not identical or symmetric in some sense. So here is the amount of time it takes to go from A to B, B to D, A to C, and C to D. So what are N1 and N2? So imagine that AB is a congested road, very narrow road, and if you are the only bicyclist there, you can actually go faster. But if there are more people, then the time taken is proportional to the number of people who are traveling on that road. So N1 is the number of people who are taking this AB path, and the time taken is 5 N1, let's say, seconds. And similarly for CD, which is N2 is the number of people who are traveling on this CD path. And AC and BD are wide highways you can think of. It does not matter how many bicycles are moving on that road, it will still take you 600 seconds. Okay. Now, everybody, all the vehicles are agents in our case, and they always want to minimize the time. So, what do you think will be the equilibrium in this case? How should people behave so that they minimize the time to reach from A to D? Think about in steps. Let us say you are the first person who is taking the bicycle. Which path should you take?
The one which has less number of vehicles.
Well, you are the first one, so there is no vehicle. Anything is fine. Let us assume without loss of generality ABD. You have taken ABD. Now, the second person thinks that, I mean, the second person is seeing that the first person is about to take this ABD path. What should he or she do?
ACD.
Will take the ACD. The third person does not matter. So, you see that all the odd people are actually indifferent between this. The even people will actually avoid what has been chosen by the previous person, right. So, what will be the equilibrium then? So, 50-50. So, all agree that half the vehicle will go this path, half the vehicle will go this path. Which type of equilibrium is this? We have two types of equilibrium. Dominant strategy or Nash equilibrium?
Mixed strategy.
Well, this is a strategy which is a pure strategy. So, your strategy is ABD or ACD, there is no mixture here. Yeah, so PSNE, right? So, who said that? Yeah, so why is this is a PSNE?
Because there doesn't exist like the dominant strategy for some person, like the even
That might not be a reason for Nash equilibrium. I mean, if you are arguing that this is a pure strategy Nash equilibrium, then you should say that why it is a pure strategy. So, unilateral deviation. So, there is only one possible unilateral deviation here. So, imagine a player who is taking, so out of those 50 vehicles, one vehicle who is taking ABD path. Now, what is the other option that he has? The SI prime that he has is the ACD path, but there are already 50 vehicles. So, if he chooses ACD, then what will be the utility there? Yeah, so certainly the time taken will be more. So, here we are trying to minimize the cost. So, all this negative of these numbers you can consider as the utility. So, yeah, so nobody of these 50 guys will try to change onto ACD, given that all other players are still playing the same strategy, right. So, that is a key thing. If it happens that 99 people are going the ABD path, then it is a profitable deviation, right. So, this is true for a very specific S minus I star, where everybody except you, 49 vehicles are actually going in the same path, using the same path that you have chosen. The other 50 vehicles are using the other path. Under that condition, you should not be changing. It is not for any S minus I tilde, because there could be an S minus I tilde where everybody, the 100 people are actually going in that ABD path. Then you choosing that ABD path is not beneficial, you can actually have a profitable deviation, right. So, this is a pure strategy Nash equilibrium. Everyone is convinced? If you are not convinced, let me know. And feel free to stop me if anything is unclear. Do not have a kind of compulsion to finish everything as long as the message is passed.
So, is there any use of the word rational agent here?
So, we are always assuming rational agent. The rationality is defined in terms of their utilities. Everybody will pick their actions such that it maximizes their utility.
So, if they are all rational agents, so they will do this only, right? 50, 49. Like all 99 won't go in the same direction.
Right,
They are
right.
rational. So,
Yeah.
is that S vector possible?
Everybody, the 50-50
If
split
there are, that is fine, but all 99 going in one direction
is not.
then they are not rational, right? So, is that vector even there in the action space as such? Because they won't take that strategy, right? All of them at once.
So, here one of the fundamental assumption is that people are non-cooperative. So, this is all non-cooperative. You
And
don't
they take
talk
the
to,
independent decision.
they take independent decision. You don't talk to your neighbor. So when the bicyclists are taking their cycle out, they are not talking to somebody else. They are just thinking, oh, so this guy is going this way, okay, so I should go that way. So it's non-cooperative games that I mean for most of this until the next week. I think we have some modules for cooperative games. You will see that when you can cooperate, when you can talk to other people, strategies become different.
But not thinking about cooperation as such, say like all 99 won't go at the like.
No, but we'll still have that strategy profile in our system, because who knows, I mean some people, if they are not rational, why should they not pick it? So this is an outcome which happens if people are picking rationally, but the strategies are all there, right? So what happens if now one player has a different set of strategies? Maybe this path is not even in his strategy space. Then the game will also change, and equilibrium will also change. So for instance, if one of the players does not have, in the prisoner's dilemma game, does not have a warfare strategy at all, they cannot develop any warfare. So then you know exactly what to do, right? So that's a kind of a setup. We'll still have this capital SI as the fundamental definition of our game. Depending on depending on those definitions, we'll argue what is the equilibrium, dominant strategy, or pure strategy, Nash equilibrium, or mixed strategy.
So strategies are independent of the rationality of the agent. Only
Yes,
the
yes.
utilities will be different.
Yeah, so that is given. So you cannot change the setup of the game. We'll see in mechanism design you can change that, but yeah, for now we are assuming that everything is given to you. Okay, so just quickly finishing off this particular equilibrium. So what is the time taken by each of this bicycle to go from A to D? 850, right? So 50 going in this way, so together 850. Okay, so now the university planner, the dean of infrastructure planning and support, comes in and thinks that we will build a very super fast shortcut so that people can now travel faster. Okay? So let's imagine this is like a teletransporting device. The moment you are at B, you are at C. Okay, so it's and it is unidirectional. You cannot go in the other direction. So from B you can go to C in almost like negligible time. Okay, so now how does the equilibrium change? So what will be the argue in the very same way? Which path should you take if you are the first bicycle in the morning? ABCD, right? So that is giving you 5 plus 5, 10 seconds. Second guy? Okay, third guy? Suddenly something has changed, right? 99th guy? I have chosen the numbers in such a way that even 100 people goes there, AB is still a lucrative path. Okay? And yeah, so you can only split here, but you cannot split here. So you anyway encounter this cost and then this cost. So you consider, when you are considering the path between these two different ways, so you have the option of ABCD, ABD and ACD. These are the three options that you have currently. But even if you know that 99 people have already traveled in this ABCD path, which path should you take? You are the last person. Still ABCD. So everybody is sort of convinced that in this equilibrium, or whatever equilibrium we are in, it's very reasonable to assume that all the 100 vehicles are going in this ABCD path. What type of equilibrium is this? What? Sorry? Dominant. Why? So yeah, so you see now the difference, right? So S minus I tilde can be anything. So even if the other people are, so let's say other people is going ABD path or ACD path, doesn't matter. Your shortest path is still ABCD, right? You see this, that so it's better if player goes, some of the people actually take some other path, because then it will reduce your time. So if someone is taking ACD path, they don't congest you on this AB path, so it's better for me. Still I'll choose ABCD. If someone is taking ABD path, then they are not congesting this way, so it's better for me. And even if all the 99 people are choosing ABCD path, still it is better for me to go ABCD, right? So S minus I tilde, for no matter whatever happens, I'll still choose ABCD. So, this is a dominant strategy equilibrium, right. Everybody convinced about this? Okay. What is the time taken? All 100 people are using the ABCD path.
500.
500 in AB, then for CD? So, 1000. So, is something wrong with the planning, the Dean of Infrastructure Planning and Support they have created? So, it seems like you have created a super fast highway, it should reduce the congestion, but it has actually increased. So, this is exactly where the strategic behavior comes in, and this is not a kind of a toy example. This kind of thing has actually happened. People in certain cities built bridges which was supposed to be reducing the congestion. They had to break this out because these two resources are underutilized, zero utilized, and this resource has actually increased the congestion. So, design is important. So, that is you cannot just add resource blindly, which some of the dean's office do. So, yeah, if you are interested, so this is the link. So, the slides will be available. So, if you want to know more about this, you can go to that link, find out more such interesting examples, at least look at the notes, lecture videos, etc. Okay, so talking about design, now we are actually shifting our gear from the analysis. So far our game was given, and I think someone has pointed out that this is where we do not make assumptions about what is available to us. Given this, what is the predictable outcome? Now, we are going to design. So, we have some objective to satisfy, let us say reduce congestion, how we can design the game such that certain things happen. So, I will start into the because for the later part of today we will be talking only about auction. Let us start with the auction example. So, what is an auction? The traditional way we know it is that suppose there exists one indivisible item like a painting which is to be sold by an auctioneer, and there are multiple individuals, and by this height of this bar I mean that how much they really value this painting. So, maybe in this case the third individual is art lover. So, he values that painting very highly. The second one is this individual, she likes it less than that the third agent, but still medium, and he has very little value for this painting. So, this is the truth, and we do not know it, or at least the auctioneer does not know it. These are something that is privately held by them. So, for instance, how much I like a specific painting, it is some private information. I will reveal that only if the game incentivizes me to reveal it. So, that is the crucial difference that we will be making. In some sense, we want to elicit this information in a truthful manner. So, the question that we want to address, and this is because mechanism design starts with an objective. In this auction example, our objective is, let us say, to allocate the object to the individual who truly values it the most. So, in this case, if this was the true state of the world, which we do not know as an auctioneer, I should give this item to the third agent. If my game is not properly designed, they might, so what I have access to is not these true values, because they will possibly never reveal the true values, and nobody can look into their minds and see what their values are. They can be only asked to reveal their values. So, they can report certain things, and that report could be different from what their true values are. This is the premise that we are working with. So, suppose you value the painting 100 rupees, you can say 200 rupees, nobody is stopping you, right. My mechanism has to be defined, designed only on top of what you have reported me, right. And as before, our utility in this case, imagine that the auctioneer sells the object, that is, it allocates the object to some agent and also asks that agent to pay a certain amount of money. So, the value, the true value that this agent gets, if that item is allocated to that agent, that is their value minus the payment that they make. This is the very simple way. So, if I value the item as 100 rupees and I get it for 80 rupees, then 20 rupees is my net payoff or profit or utility in this case. Okay, so I am going to give you one specific auction. So, does anybody know any, do you have any ideas of how we can solve this? So, our objective is to ensure that they reveal their things truthfully in some equilibrium such that so you give the item to the person who truly values it. If you already know the answer, don't let others try to attempt it. So, is the problem clear? So, they have some values, these are all invisible to us. I want to give the object to the agent who truly values it the most somehow. So, I can only ask them that they bid for this item, this painting, and I also can decide whom I should give the item to and how much payment I should charge that agent or all the agents. Do you think that there is a way that I can ensure that they reveal their true value for that object in an equilibrium of some game?
Payment is fixed, right? So
No, payment is not fixed. Payment can be dependent on what you report.
but after everyone reports, then we will decide the payment and.
So, therefore, payment is a function of what people have reported. So, if the reporting profile is like V1, V2, V3, then your payment could be something. If it is V1 prime, V2 prime, V3 prime, your payment could be something different. So, payment is a function of this valuation profile to some real number for every agent.
I mean, I can set a threshold, then if some agent agrees to it, then it means that they value it more than the threshold. So, we can guess some kind of value.
Sure, but what if more than one person bids above that threshold? What you are saying is I set a price for this painting, and then the mechanism is still not well defined, because there could be all three people who are bidding above that value.
Yeah, then I can set the threshold to the maximum.
Then you can change it.
Yeah,
So,
and
this
then keep
so
repeating.
yeah, so we are looking for something which is one shot. I mean, this is not like you can update, right? So, in typical auctions, yes, you see those type of things that you start with an I think this is a good idea to think about this. If you have ascending bid auction, so you ask people that this is the minimum selling price, we cannot sell it below that. Now, people bid and they compete against each other, whoever is the highest bidder currently, then they can also change their bids later on. So, here we are looking at a much more to keep the setting same as the single shot game setup. Everybody can bid exactly once, and you will have to decide based on those bids what is your allocation policy, whom you should give the item to, and how much you should charge.
So it will be simultaneous, right? All
It has to be simultaneous, yeah. So, everybody, let us say they put their bids in envelopes and gives it to the auctioneer. The auctioneer has to decide on what is that, what to do with those bid envelopes. Have to open it, decide it, but that rule has to be defined beforehand. You cannot say that the rule is going to change, because their strategies depend on that.
So, what's the objective of
The players,
the auctioneer? He wants to give it to the person who values it the most, right?
right?
But the person who values it the most can give a very low price.
That is not obvious unless you define what the mechanism is, right?
Yes.
Why should he reveal it?
No, I'm asking what if the person who values it the most?
So, we are assuming that these players are those game theoretic players who are trying to maximize their utility, which is the value minus the payment, right? And in a way, I want to ensure that if they report their valuation in a truthful manner, then only they maximize this. Let us take an example and then we will analyze this, because that is what we are going to come to. So, let us take this particular protocol. So, I am telling everyone beforehand that you can bid, put your bids in your envelopes, give it to me. The rule is that whoever, so when I open this the bids, the envelopes, whoever has the highest bid, I am going to declare that person as the winner. If there is a tie, I break the tie arbitrarily in favor of one. Now, this interesting part is I am asking you not to pay your bid, rather than the second highest bid, right. So, in a way that if everybody has revealed the values in this way, so if their values, so whatever the value is here, they have revealed it in that way, then the third person will actually win according to this protocol, and he will pay the value 1, which is the second highest bid, right. Okay. So, this is called the second prize auction, and I will try to argue at this point non mathematically, later we will argue mathematically why this will actually satisfy this objective, that will give the individual who truly values it the most in a way that the person who has the highest value will also bid highest.
So here our aim is also to give the person who values it most, and also we want him to maximize his value minus payment.
So that is always the case.
Like, because if I remove the pay second highest bid, then also like the value. So in case of time, maybe like if we remove the pay second highest bid, so that agent is not able to maximize, but our objective is still done, right?
So what do you? So you don't have your protocol to have the second highest bid.
Yes.
So then, what is your payment scheme then?
Only highest bidder wins, and whatever he has
pays 0.
Whatever he has bidded.
First price.
Yes.
So pays. Oh, so what he has bid.
Yes.
Okay, so then why should actually he bid his true value?
Because
he knows that here, okay, so let's make our target very clear, that agents will be truthful, that is they will reveal their valuation. So, you want this as the equilibrium guarantee, that regardless of what other agents do, they might report their true values, they might report something else. So, this is in the spirit of that dominant strategy, right. So, truth telling will be a dominant strategy for all these players. Right. So, do you think if I charge everybody their own bid, they will actually bid their true value? Why not?
They would want to maximize value minus payment.
Right. So, but
So they try to bid lower than what they actually value.
clearly that is true, but up to what level?
they won't get
The second highest.
So, if this player knows that, okay, so there is nobody who is above this value, let us say 80 rupees, and my value is 100 rupees, why should I even bid 100 rupees, because then I will pay 100 rupees, but I can do 80 plus some 80 rupees and 50 paisa, and that will actually give me the item, right.
The players would know values of.
So, that is why we are assuming that regardless what other players are do. So, you assume that you have the complete information about other players. The auctioneer does not know their values, but as players you have everybody else's information, which happens in, so maybe the spectrum auction, one company knows how much roughly the other companies are valuing this particular place or a particular spectrum, right. So, they know their valuation. So, we want to make our equilibrium guarantee much stronger. We want to make sure that no matter whatever the other players are doing, it is still going to the agent who is valuing it the most. So, they will not reveal their valuations truthfully. That is what our objective was.
So he pays the second bid after he sees the first bid, right?
No. So, it is all simultaneous. I am just assuming that when he takes his simultaneous decision, when he puts his bid inside the envelope, he knows what other people have bid, let us say. He actually can see other people's bids.
So he bids the highest to show that he has the highest value, essentially.
We are going
value
to.
minus payment is an affordable loss. Like he's okay with the loss.
So, you are arguing why this is the dominant strategy equilibrium, right? Okay, yeah. So, let's do that. So, yeah. So, the argument is, so suppose I am looking, I will take two viewpoints. One is the winner's viewpoint and also the loser's viewpoint, right? Because the loser can actually bid higher and get that object, right? So, the second prize auction somehow should prevent that person, in this case this player 1 or player 2, not to bid so high. And why is that not a good option? So, let us look at the winner's viewpoint. Assuming that they have reported whatever they have reported, it does not necessarily have to be their true values. They could have reported something else. The second prize auction is ensuring that your payment, the second part of your utility, is not dependent on your valuation. So, your action does not change your payment.
So
does the bidder is the bidder concerned about his or her profit?
Of course.
Yeah, then why would they give a high payment if they have a corresponding lower value? They wouldn't do that, right? Because their payoff will be less.
So you think about from the viewpoint of player 3, what action does he have? What options does he have? So he cannot change what player 1 is going to bid. He can only change his own bid. By changing his own bid, can he change his payment? The answer is no. He cannot change his payment. So imagine he overbids, right? So here the assumption is that, I mean, of course, this is true, that if you get the item, you experience your true valuation. It does not mean that if I bid 200 rupees, my value for the item becomes 200 rupees. It might just get you the item, but your valuation will still be that 100 rupees which you truly value for that painting, right? So if you overbid, you can potentially, I mean, you were winning earlier, you are still winning the item, and your value is still that value 3. Right? Your payment is not dependent on your action anyway, so you are still paying the same amount. Right? So the difference is still the same even if you overbid. What if you underbid? Up to this point, you don't change anything, you still win. Below this, you stop winning. So earlier you were actually getting this positive, so this amount of positive utility, because value minus payment was positive, you are winning this. Now if you go below this dotted line, then you actually lose it, where you don't make any payment, you don't get any value. So the value is only obtained when you win that object. Your utility suddenly goes to 0. So that's not a profitable deviation either.
So the threshold is not value 1 but payment 1.
Threshold is the second highest bid. So whatever people have reported, so they could have reported something else. Okay.
Right,
Yeah. So the second, because I can only see their envelopes, and when I open it,
argue that it's the actual value.
it does not need to be an actual value. So that is why S minus I tilde, right? So their action is like what their reported values are. So no matter whatever they report it truthfully, untruthfully, it does not matter. You should not change your valuation if you are the winner. So we have argued for the winner's viewpoint. Why should it be the best response to be truthful even for a loser or non-winner? Okay. So imagine, so the only way, so if this agent reports anything below, so imagining again that these guys are reporting whatever these bars are showing, up to this point he never wins, this agent, she never wins. The only way she can change the outcome is when she reports something higher. Why is this not a good idea for this agent to do? So what will be the payment now for this agent? So the payment will be now the second highest bid, right? So this, if you draw a line for value 3, it wins that object. Her true valuation is still value 1. She makes a payment which is larger than her true valuation. So she can get the object, but the payment is so high, it's more than the value. It's negative. It's better to not win the object for that agent.
So why do we need the assumption that players know each other's?
Because we want to ensure dominant strategy.
Even if they don't know what others are bidding, the dominant strategy is still to bid your value. Right?
True, but I mean the equilibrium guarantee is a little weaker, right? So we can say that it's also a Nash equilibrium. The question is what people know. The action that they take is dependent on what they know, right? So if they know nothing, let's say they know, then we can't say anything about what their actions should be, right? Because they do not know anybody else's valuation, so they cannot actually calculate what this utility is, right?
No, but they can guess. Like if I bid something higher than my value, okay, and by like accidentally if I end up winning, then I will end up getting negative utility. So I should never bid higher than my value.
No, so it could be that others value is still above.
Yes. That's case one. Like another case is,
Yeah.
if I don't bid as much as my value, if I bid slightly lesser, then I might not win at all.
Fine, but that is automatically assuming that, so the assumption of dominant strategy, right? So, whether you think it in that way, still it is a dominant strategy for them to bid their values truthfully.
Yes.
Right? It is much stronger than saying that if the other players are playing in a certain way, only then it is better for me to reveal truthfully, otherwise I can gain by lying. You can actually do this exercise with that thing that you just said, that you bid your own value and you pay your bid, right. So,
Paying second highest.
here, but that first price auction, so of course this is second price auction, there is a first price auction. The analysis is not as straightforward as this one, but you can argue that there also you can come up with a little weaker guarantee of equilibrium, where people will reveal their valuation, which reveal their bids, which is not exactly their bid, something else. Okay. All right. So yeah, so you can see that even when yeah, so this values are different, the same argument will actually go through. It does not have to be the case that they reveal their values truthfully. Any of the agents reveal their value truthfully, still it is better for every agent to maximize, to reveal their valuations in a truthful manner. So, we will analyze this game in further detail later on. Let us just move on to things which we require. So, any questions about this? We will just formally now address this with some notation and try to argue it more mathematically. Okay, so let us get started. So, try to get to at least the setup ready before we break. I think we have around 15 and 25 minutes. Okay, so the mechanism design, as we know that the objectives or the desires are set, and then the ask is to set the rules of the game. So, for instance, there are many examples. So, we looked at the auction which fits in the licensing of scarce resource like spectrum or cloud, but there could be other examples, and we will see this type of examples later in this school, matching students to universities where we do not use any sort of payment. So, we had a feature called payments, but that is not necessary in all the, it is not also possible in certain settings. Election we do it, I mean we just had the national election. So, how to elect the individual whom everybody values the most or something of that sort. Okay, so the general setup that I will be using for this today's and also tomorrow's all the lectures is that we have this n. You can just think about that as the square bracket n coming from yesterday's lecture. This is the set of players 1, 2, 3 up to n, small n. Here we have certain set of outcomes, right. So, connecting to our auction example, which item to be allocated to which agent, or who will be the winner in an election. This is, we are going to abstractly say that this is a set of all possible outcomes. And we have introduced something called this the agent's type. So, an agent has a type which is denoted by small lowercase theta I, and the collection of all possible types is denoted by the capital theta I. Okay, so, that is the setup. Now, based on this, I think this question came up yesterday. So, I just want to make sure that how this type actually manifests their preferences. So, the types are going to say that how much they value or prefer a specific item. So, this type can be, that is why it is very abstract. So, you can think of the theta I like a preference order. So, in elections I can potentially have, I mean we do not do the elections in that way because we have a different protocol, but we can think of, let us say I have an agent A, I prefer this candidate A over B. Everybody from that direction can see this, otherwise I can write it on this side. So, yeah, so let us say A over B over C. So, this is like my theta I, that is I prefer this candidate the most, the second preferred is B and the third preferred is C. This could be a kind of a description where I am not saying how much I value A, right. So, unlike the setup that we were using, that we have an utility or a kind of a number associated with it, we can have an have a preference which is just telling me the ordinal order. I may like specific type of a sweet, maybe ice cream more than rasgulla, or maybe the other way around. But I cannot specifically say that how much, is it 80.25 or 70.15, I do not know. I can just only order them. The second setup is the cardinal setup, where we can assign those numbers. So, under this setup we have this utility function ui, which maps that outcome. So, whatever outcome we take from this set x, and what is my type, depending on that I can assign a real number to it. So, formally this will be a kind of a mapping of this outcome. So, let us say in the auction example, agent I did not win that object and his type theta I was something. Then if he did not win that object in that outcome, then his utility becomes 0. If he wins that object, then theta I is his valuation, something like those numbers that we have seen in that diagram. Okay, so this is the setup that we will be using for cardinal preferences, because we are discussing about auctions, the cardinal setup, but it is good to know that the ordinal setup also exists, particularly in the setting of voting, which someone will cover. We will see this ordinal preferences rather than the cardinal preferences. So, there is another setup which is called interdependent. We will not use it, so let us not discuss it. So, the examples like this, one example from the ordinal setting, where x is the set of candidates, which candidate you choose becomes the winner. That's so, if I have players A, B and C, x is the set A, B, C, one of them will be chosen as the winner. And this theta I is the ranking over those candidates, just like the way we said. That order means I prefer A more than B more than C. Okay. Yeah, go ahead. Okay. All the slides will be available, so you do not have to, I mean, if you miss something, yeah, do not have to worry. Okay. So, in the cardinal setting, we have the single object allocation. We are using this running example. So, you can think of this outcome, this capital X set now is a collection of two things, both are functions. So, A is a function actually, okay. So, one specific outcome you can say as an vector of allocation, an allocation vector and a payment vector. So, this lower bar says that this is a vector. What does this first vector mean? Let us say these are a vector of length n. Each of these numbers, each of these entries are either taking value 0 or 1, denoting whether that agent has owned that object or did not win that object. And naturally, we also need this condition that the sum of these AIs have to be less than or equal to 1. If it is the sum is 0, that means the item is not sold. That is also a possibility. Yeah.
Capital theta I in the example of voting.
So, it can have all possible. So, suppose there are m candidates in the election, the capital theta I will be all m factorial possibilities if we are assuming strict preferences. If there are ties, then you will have more. So, you can have something like I may not be able to say, so I prefer A more, but between B and C I am indifferent. This is also a kind of a preference. If you have this kind of a thing, then you have more. But if I only assume that my preferences can be A, B, C, B, C, A, or I mean all the 6 cases in this case for 3 agents, for m agents all m factorial options.
Can you explain the single object allocation?
So, single object I will have to frame it in this framework that I have used, right. So, there is an outcome. Now, the outcome in a single object allocation or this auction example, I will have to decide 2 things. One is the allocation and another is the payment. How much I am charging. So, whom I am giving the painting to and how much I am charging all the players.
So this is a model, like the voting thing is a model.
Voting thing is one of the examples of the ordinal preferences.
So how is this single object? Like I cannot, like what is x equal to the A and P? What is P there?
So, P is the, okay, so I have not come there.
Oh.
So, P is the payment vector. So I am telling you that, okay, so I give the item, so exactly one of this, at most one of this item, this entries will be 1. So suppose I give it to the 5th agent, and I have a payment, so maybe I can give, so I can charge payment. So here the idea is that if you have an item, you are making this amount of payment charged to agent I, that is that agent is paying the auctioneer that amount. So I can have, let's say, 0 for everybody else, and for the 5th agent some amount of money. Yeah, so I mean the model is generally you can have any payment. So this now how we will actually compare between these outcomes, because finally I will have to, if I give you 2 different outcomes, let's say in the election case I declare B as the winner, right, then I prefer that less if A was the winner, right. That I can do a comparison, but in an ordinal way. I cannot give a number associated to it. Right. So I like B more, but I do not know how much I like, sorry, I like A more, but I do not know how much I like A more than B. Maybe they are comparable, but I do not know that. So that is a different model. While here I have this utility function, right. So this theta I, in this case the type is telling you that how much you value for that object. So if you win that object, you can actually assign an utility function which is telling you that x, which is a collection of these 2 things. If you, so ai is that indicator variable which is telling you whether you win or not. If you win, then you get this theta I, otherwise 0. So suppose I did not win the object, my valuation for that object is 0 minus the payment that has been charged by this outcome, right. So in that case, let us say the value was 100 and you are paying 80, then your utility would be 20, and that you can precisely say in terms of the real numbers. Unlike the case where in the ordinal setting, we can just make ordinal comparisons, that I like this more than that. Here I can actually say very quantitatively between one x and let us say some other x prime, right. So how I can think about this is that I have 2 different outcomes, right. So let us say an x which has, let us say, only 3 players, A1, A2, A3, right, and the payments are P1, P2, P3, right. This is one x, right. So this tuple of these 2 things, that is how I have written this x as. Now suppose there is another outcome which is giving you the same allocation, P1, let us say P2 minus epsilon and P3. So it is charging a little less for player 2. If you are player 2, let us say player 2, between x and x prime, you can clearly say something, right. So x and theta I, this is the function it is. So u2 of x prime comma theta I. Can you put some inequalities between? This side is greater than, sorry, the right side is greater than this one, because you are charging less to that agent, right. It will be a weak inequality because you might not get that object, in which case it does not really matter. Yeah, if the payment, no, so the way I have written it is that the payment is charged irrespective of whether you win or not. But yeah, so you can see that the first part A2 theta 2 is going to become the same. So in this case A2 theta 2 minus P2, where while here it is A2 theta 2 minus P2 minus epsilon, so plus epsilon in this case. Actually this will be a strict inequality in that case if epsilon is positive. Right, yes. Yeah. So yeah, so we can actually compare between 2 outcomes in this space. So which we were also possible to compare in the ordinal world, but the comparison was ordinal. So if I said that agent B is the winner, I prefer that less, but that preference I can only represent in terms of ordinal preferences, not as precisely in terms of real numbers as this one. So we will be mostly working with this premise because we are dealing with auctions. So
general model of mechanism design? The one
I am coming to that. Yeah. So how you can? So this is just for a specific outcome. The question is how we actually decide depending on their types, right? So the question is, I have this outcome. So I did not tell you how I came up with that outcome. The point is that if you tell me this theta i's, I should have a function which is mapping to that x, the space x. That is exactly the mechanism design problem. In fact, the very next slide. So the designer's objective, what we have designed, we have told so far, that I have an objective to give the item to the maximum valued agent, right? We can capture that and also many other things by defining a function which we call the social choice function, something like the recipe that we want to satisfy. We have to cook the food, my outcome should be something like this. So this f takes all these inputs from each of these agents. Remember that this the mechanism or the designer can only look at what has been reported. So there is no reason to believe that they will report their types truthfully, but if their types were truthful, then I would have liked to do that. Okay. So let us say in the auction example, if their types are of this kind, then I want to give the item to the agent who has the maximum value among these, right. That can be captured using a social choice function. Okay. So yeah, so I think I have given the examples in voting. So let us say, yeah, so there each of these theta i's are rankings over this let us say 3 candidates or m candidates. Now if there exists a candidate who beats everyone in pairwise contests, so you take that A, compare with B or C, and if it turns out that it beats everybody else in pairwise elections, you just delete all the other candidates, count how many votes this guy got and the other guy got, take that, and if that person beats everyone else, then that must be chosen as the winner. It might not happen. So you might have a preference profile of these agents where there does not exist any candidate who beats everyone else. It may not happen. In that case, the social choice function is silent. You can choose anybody. Okay. So this is one example from the ordinal world. This is from the cardinal world. So here, suppose I want to choose a public project. So in the city, I want to build a bridge or a museum or a road, whatever, and those are my outcomes. Every agent has a value associated with those outcomes, right. So think about that x as bridge, museum or a street, and that gives you a certain valuation. I want to pick that outcome that maximizes the sum of the happiness of all the agents. So f theta is the argmax. So if most of the people think that bridge should be built, we should build the bridge, and so on. So these are some examples of social choice function which is mapping. Now this is part of our mechanism. We have to somehow come up with some schemes in our auction setting how we can actually achieve this social choice function in an equilibrium. Okay. So the question that we are going to address in mechanism design is how can we create a game where theta, that the true theta. So remember that they can only report what they can report anything, but we want to have that the true theta. So here from going forward from now on, we will always use the theta to be the true values, theta prime, theta tilde, all these things could be anything else. It need not be the true one. This has to come out as an equilibrium, could be a dominant strategy equilibrium, could be a Nash equilibrium, we will talk about that later. So if I can achieve that, then our f theta is the outcome which is desired, right. So if I can find theta, then I can actually calculate, because this social choice function is clearly defined and everybody knows it. So everybody knows that we are trying to build a social welfare maximizing thing. Yeah, so that is desired. So the answer to this question is essentially we need mechanisms. Okay.
Sir,
yeah.
So in this, suppose in the example of public project choice, each builder has some kind of preference. Like some builder prefer.
Here the players are not builders. Here the players are the citizens.
Sorry, yeah. So like each builder has some citizen has some kind of preference,
Yes.
and they give their preferences.
Their
and
values.
their valuation. Now we have to choose.
Which object, which public project to build. So let's say, yeah. So just to give you a kind of a running example. So suppose I have a bridge, a park, and street. Okay. So these are the three things. So every agent can give me, let's say theta 1, which is a vector of 3 numbers. Let's say I like bridge a lot, park maybe 90, and street is 20. Right. So theta 2 is something else, right, the numbers. Now what I will do is I will take the sum. So when I decide this particular thing, so for this example I take the whatever they have reported, I will take the sum of these numbers and compare whichever is to be built. Okay. So this is the example.
That's f of.
So this is the set, this x in this case. So x in this case is B, P, S, whichever outcome I select, and their types are these tuples of 3.
Okay, so f will take all the preferences, and
Yes.
then it will give me
Pop out.
something belonging to x.
Yes, exactly. So if you have this up to, let's say theta n, the function, the social choice function, I want the social choice function such that it maximizes the sum of the happiness of all the players. Right. So f of theta, it will take this theta 1, theta 2 up to theta n, and it will pop out some of this outcome. So let's imagine this is a deterministic mechanism. So it can only decide that build bridge or park or street, not a mixture of any of them. Okay. So we'll yeah.
Theta double here, like what would theta? F of
Theta
small theta.
f of theta, yeah. So theta 1, theta 2, yeah. So yes, I am just using theta to mean the entire vector. We'll also use this. I mean, like we have used s, it is s minus si s minus I. So similarly, I will be using theta to mean theta 1 to theta n, which will also be sometimes shortened as theta I, theta minus I. It's all very standard notation. Okay. Yeah.
Example of voting, how is the social choice function defined?
Oh, that is something that we have decided beforehand. It's not part of the mechanism. We want to satisfy this. Let's say when we say that this voting, the candidate who beats everybody else, you write the social choice function in that way. So if there is, so for certain preference profiles in the ordinal world, you will have that agent who beats everybody else, that happens to be the winner, right? So you can capture this text in English in some function. Similarly, this can also be captured by some function, right? So that's, so in this case it's easy to write mathematically. Here it is a little difficult. It's not so easy as this one, but that is something that we are actually starting out as our objective. I want to satisfy this. Now the question is, can we actually design a mechanism where in the equilibrium everybody will reveal that theta truthfully? We have already seen the truthful revelation kind of a example, and if I can do that, then every rational agent will reveal their types truthfully and will satisfy the social choice function. Our objectives are met. That's all. Okay. So before we break, we have roughly 2 minutes. I just want you to leave with 2 different definitions, and we'll believe we have only right. Okay. So I'll start with the transfers in the after the break. So dominant strategy truthfulness, it is actually saying, we already know it, the truth telling is a dominant strategy. Okay. So truthful in dominant strategies, that's how we are going to call it. So remember that your f takes that the function, so f is that function which is mapping your theta, the vector of theta, theta 1, theta 2 up to theta n, and popping out one specific outcome. Remember, your utility was a function of the outcome and your true type. So wherever you will see here, the second entry will always be the true type of this agent, because anyway you will always experience your utility with respect to your true type. like if you win that object, then you experience that valuation. You might misreport it, and thereby this mechanism can get you something else. So, maybe if you have reported theta I, then you possibly get the item. If you report theta I prime, maybe you do not get that item, somebody else gets that item, whatever that is. So, by changing your reported type, you can only manipulate this outcome function or the social choice function, but you cannot change this one. We are always evaluating your utility with respect to your true type. What this is saying, and notice this qualifiers again, these are the, so in this world their strategies are their types. So, they can report their true type, they can report something else. So, for every type reported by the other agents, they might be truthful, they might be misreporting, just like the example that we saw in auction. The utility, when you report it truthfully, you get more, at least as much utility than any other utility that you can possibly get by misreporting. So, this is true for every theta minus I tilde, theta I prime, and also for theta I. So, because we do not know what your true type is, if your true type happens to be theta I, then this inequality should get satisfied. That is why you also need a for all theta I, and of course, it has to be satisfied for all agent. It will take a bit of time to sink in, but I think you can write it down, stare at it, and then try to understand, and if there is any questions, we will discuss this in the tutorials again. So, this is the dominant strategy version, and I just want to give a kind of a Bayesian extension. So, you can see the difference. So, here what we are ensuring is that it will be true for every theta minus I tilde, but I think someone has pointed this out. So, what if you have some information about the other agents? So, you can actually propose something which is a slightly weaker, which says that if I, so maybe I am an agent who know that, okay, so this particular contract is very valuable for me, so is very valuable for other players as well, right. So, if I am a service provider of internet, then this spectrum, if this is more valuable for me, I also have some information how much valuable, or at least the distribution of how much valuable it is for the other agents. So, even so this is a weaker guarantee, which is saying that even if I do not know precisely what their types are, I can still look at the expected utility of mine and expected utility when I misreport. So, still notice that I am reporting my type truthfully, and this ceases to be a function of theta minus I anymore, because I have already taken the expectation with respect to theta minus I. So, here there is no for all theta minus I anymore. It is only comparing between if I report theta I when my true type is theta I, and what happens if I misreport it to theta I prime. So, then in that case we are going to say that this is truthful in Bayesian strategies. Can you draw a connection between this dominant strategy incentive compatibility and BIC, Bayesian incentive compatibility? Which one implies which one? Dominant implies this, because there you are ensuring much more. You are ensuring that for every theta minus I, even if you take the expectation, it will still get satisfied. But you can create examples that where it is Bayesian incentive compatible, but not dominant strategy incentive compatible. So, therefore, it is a weaker guarantee. In the cases where we cannot guarantee DSIC, we might go for a weaker guarantee like BIC. Okay, so let us break for tea now and come back with this transfer setup, where we will make this ideas that we have discussed more formal. Yeah, my objective is to go to this VCG mechanism, because this is one of the classic mechanisms for multi-item allocation, and also applied in various other settings, internet advertising to be specific, and we will see all the details of VCG by the end of this end of today.